Good afternoon everyone and welcome to this thesis defense of Lakshminarayan and Nada as his friends call him and Lakshmi as some of the people call it. And then joined our, actually he finished his BTech from IISc Nagpur, which is now NIT Nagpur. Was it IISc? It was NIT Nagpur. For a ME. We took my class mechanical behavior and decided to convert, not the conversion to Christianity or something like that. But, the ME students have the option of converting into PhD, so we decided to do that and join my group. So at the time, we were working on metallic glasses, and I think Raging graduated. So I asked him to continue on. And, he did very interesting pieces of work as part of his thesis, and most of it is published, and there are still many papers in the pipeline. So he's going to defend his thesis. I would like to welcome Professor Varmale, who is his examiner, Indian examiner, and Professor J. Jiang is his public examiner. I'm pleased to report that all the examiners have said that the thesis can be accepted in its present form, so no corrections needed, so everything is fine. Also, a warm welcome to Mrs. and Dr. Ramasubramanian. Very nice of you to come here, because PhD thesis defense is really a big deal. That's why I insist Nada to shed his usual avatar and come somewhat decent. See, everybody knows, you may not know this, but that's not fair. All right, thank you.
Hello, am I audible to everyone? Thank you for the introduction, sir. I would like to now start the presentation, and so let's move on to what we are going to discuss today. So I will give a brief introduction of what metallic glasses are, and then we will immediately shift the focus to the deformation mechanisms, which are the most relevant aspect here. This is the most relevant aspect here, and then we will go on to discuss the factors that control fracture toughness, brittle fracture mechanisms, and then finally we will talk about the new class of materials called bulk metallic glass composites, which have exceptional properties. So first we talk about what's a glass, and we start with the fact that when you cool a liquid, it generally tends to form a crystalline structure. It's all the atoms have a regular formation, in a regular pattern. But when you cool them rapidly enough, there is a chance that they may sit in random positions and form glass. The major thermodynamical thing is that there is an abrupt volume change when you cool a liquid slowly. That is when it forms a crystal. But in glasses, you find that there is a gradual change, and also this is referred to as a second order transition. Now, let's immediately skip to the structure of glasses. As you know, there is a lot of randomness that is present in the arrangement of atoms. But this randomness has also got some short-range order, as in when you look at a few atoms in a cluster, they do have a particular organization. So, for example, if you can see this particular work by Daniel Britton, where he tried to characterize a structure wherein a cluster of atoms are sitting in an FCC type of fashion. You see the dotted blue lines and the other ones. He tried to make clusters sit in a particular form and then tried to build a glass structure out of it. So there are other schemes, but we should not go into the detail except for when it is required. The interest in glasses has started mainly because they have exceptional mechanical properties. When I say mechanical properties, I am talking about things like excellent resilience. For example, it has got a high elastic strain to failure, it's about 2%, much higher than any other conventional crystalline metal. And they have, they also have a very high yield strength, about 2 GPa, while your normal metals or even very well-made steel or a titanium alloy would have something like a very good steel, for example, would have something like 1 GPa. If you have bombarded with all sorts of treatments and used all sorts of pesticides, that is kind of okay. But here you naturally get 2 GPa as the yield strength. But there is, as you can see, there is a problem that if you try to load it in a tensile fashion, it breaks catastrophically. That doesn't happen in compression. As you can see, there are some sort of lines that are forming here. We'll come back to what these lines are. But these lines are shear bands which can propagate in tension unhindered, since there is no microstructure to prevent the shear bands from going off. And in tension, this results in catastrophic failure. That is, you don't have any extension after it yields. But in compression, the loading is, so there is no instability which is there in compression, which is why your specimen can actually deform pretty decently, and you can have formation of multiple shear bands, and you have some form of strain to failure, plastic strain to failure. Now, theories of plastic deformation, I would briefly talk about what from 1970s to 2000 to the present. There are some 4 theories which have been proposed. All of them, so some are based on the fact that the phenomenological aspect of glasses represent something which is very similar to diffusion. So if you see the movement of atoms from one place to another under shear can also be described as a diffusive process, which is what Franz Papen first did in 1977, and he was able to map this to the deformation of glasses with the various in different strain rate and different temperature regimes. He was able to make a deformation map. Following this, I would say, I think at the same time, but around the same time, Argon decided, or Argon proposed, that it is not about the motion of a single atom, but rather the motion of the cluster of atoms which are sitting maybe above or below the plane, or perpendicular plane. There is no crystallographic plane here, but it's a motion of atoms which undergoes shear, sudden shear, to accommodate external strain. And he was able to then define an energy barrier for that. That is, this motion from one saddle point to another saddle point can be represented with this barrier, and it contains a dilatational term, which means there is an effect of dilatation. There is an effect of hydrostatic strain here, which basically means that your cluster has to undergo some kind of dilatation, after which it can undergo shear. Now, after this, in the 2000s, Sammer and Johnson, they after using the ideas from the Stillinger and Divinity inherent state models, where they talked about potential energy landscapes, as in every system or any disordered system would be sitting in one of the wells of a potential energy landscape, and they can escape if they are provided sufficient amount of energy. And depending on that, they were able to develop a model where this energy barrier to cross over from one potential energy state to another was described by this equation. Moving on, in the same tone, alpha and beta relaxation models, which are generally found in polymers, can also be applied to glasses. And here, in glasses, it is described as a process where you have a shell, you have a group of atoms. And okay, first we can consider glasses to be as a very tense formula. It's a very tense state, okay, and then it wants to relax to a state where it has got the lowest energy. So when we try to apply stress, the viscosity of this glass starts increasing. So that is represented by beta relaxation, as in the atoms start moving within the cluster, and then after a critical point, these atoms gain so much energy and velocity that they percolate through the structure, and this is known as your alpha relaxation. So this beta relaxation talks about hopping within a mega basin in the potential energy landscape, and your alpha relaxation talks about jump from a mega basin to another mega basin. And jumping from one mega basin to the other mega basin actually means that the internal structure has completely changed, and we'll come to some aspects of that later. So microscopically, that was the picture. Macroscopically, all these STZs collectively form something called as a shear band. As you can see here, a better picture is here. This was one paper by Marius Dimitrov, whom we have collaborated with in the recent past. And he shows that when there is a crack in a metallic glass, shear bands, and when it's loaded, shear bands can form in a very dense fashion. And this actually provides a lot of crack resistance. And we generally think that shear bands, as in the case of tension, can cause catastrophic failure, but it is also the only means of plasticity in metallic glasses. Now we'll talk about the first part of my work, which is factors affecting or parameters affecting fracturability. The idea that was evolved by Greer and Lewandowski was that they talked about the criteria used in crystalline metals, where they said that if you have a highest resistance to shear, a lower resistance to shear compared to resistance to dilatation, you will have plasticity will be preferred, right? Or you will have, or rather, your material will be ductile. So using the same concept here, mu, which represents shear modulus, and B, which represents the bulk modulus, this ratio should be below a critical limit for your glass to be ductile or tough, not ductile, tough. So this was the criteria proposed by Greer and co-workers. The only problem was that this criteria could not be applied to glasses which were annealed or structurally relaxed. So there is another group, I would say Professor Ramamurthy and his workers, who had first suggested that elastic parameters are not the parameters that control toughness, but we should rather look at things that are related to plasticity. And then he had an idea that free volume or reduction in free volume rather would lead to loss of toughness. And he had measured using spherical indentation and compared in an as-cast and an annealed glass, where the shear band numbers in an annealed glass are less, and they found that this is much brittle compared to this. So the formation of shear bands actually enhances plasticity. Briefly, I will give this introduction because we need to understand the effects of temperature in the coming slides. And that is, when you have a liquid and you cool it really fast, your atoms are not able to come together in a perfect way, so they get trapped. There is some reduction in the amount of spaces you see from here. And then if you keep continuing the cooling, you will form something called a metastable glass. Now, if you use some form of intermediate cooling, you will have a glass which is stable under room temperature. It is not under too much strain. And this glass, if you anneal for a small amount of time, not close to the TG, it goes to the supercooled liquid state. Okay, and the supercooled liquid state would have some extra spaces between atoms. And if you cool it for a long time, this can either go to ideal glass or it can become a crystalline structure. And now the ideal glass is generally extremely brittle, and a supercooled liquid structure is mostly open. And the implications of this will obviously come later. But this is the most important diagram. This is severe plastic deformation can also result in a metastatic glass. So I'll go ahead with what we have done. We took 4 alloys, all the same composition, and this is the TG, so the glass transition temperature, and then we introduced relaxation very near the TG, so some even exceeding it, but much below the temperature of crystallization. And then we saw that the toughness, and we did very short time, all these annealing times are for alpha relaxation to occur, not much. And we saw that the toughness actually increases when we increase the relaxation temperature. But the other parameters, which people have actually studied before, like shear modulus to bulk modulus ratio, actually are within the limit of the within the critical limit, which only means that they can predict that these glasses will be tough, but they cannot you cannot use that parameter to compare if a glass is tougher or how tough it will be, or the enhancement in toughness cannot be mapped with the shear modulus. In such a case, we now move on to a theory which so that we can correlate this increase in toughness with some other parameter, and that parameter is density. So that was the first thing that came to mind, because we saw that density was indeed decreasing in cases where the fracture toughness was very high. And we see that there is a correlation in literature of density with free volume, which has also been represented by the, this is, this I'll come back to later. But so the temperature of heating in the above case, like we took it near TG, is called the fictive temperature. That is the temperature of the glass, which has, the structure of the glass of the supercooled liquid regime, which has been inherited to the ground state or at the room temperature. So using that, using this, we can also find the free volume. So there is a difference in the free volume in the supercooled liquid state and the room temperature state, and using that we can calculate the free volume. So the free volume is now, we keep that in perspective. Let's move on to what other parameter can be evaluated from these glasses. So using nano indentations, that is 100 tests, we were able to measure local yield stress, that is using this equation, or rather the local shear stress, the local yield stress, and we found that initially we thought that it is actually decreasing with, as in the material which has got a higher fracture toughness has got a lower yield stress, but that is not exactly true. Sorry, we got it wrong. Material which has got a higher fracture toughness has got a lower yield stress. Yeah. So using that, so we thought initially that this is an opposing trend, because you would expect that both shear modulus as well as your yield stress, shear yield stress should go up. But then we saw that the scatter bands are within each other, and as you can see from the previous table, the yield strength also does not vary much. So we can assume that for the sake of clarity, that there is not much change in the yield stress, but there seems to be some kind of a trend wherein the yield stress is not getting affected much. So shear modulus being the important criterion here immediately comes down, because there is no variation in your yield stress, and local yield also shows similar values. I mean, everything is within the scatter band. Now we move on to some other thing where we can evaluate the toughness, that is the number of shear bands that are formed under indentation. So here we see that in different specimens, the number of shear bands, it's better we go here. So specimens which have got higher fracture toughness will also show higher number of shear bands. Also we measured the number of poppins that were seen in a single load displacement curve, and we saw that even the number of poppins increase when the fracture toughness increases. So we keep three things in mind. One is number of shear band increases because of higher temperature, and the density is also changing, which means higher free volume. The third thing is we want to consider the size of the STC. So we are moving to the atomistic aspects now, and we saw that using the nucleation rate theory developed by Shu, we were able to determine the following numbers. The number of atoms in an STC for all the cases are almost similar. But these are very reasonably close numbers, because in an earlier experiment as seen by Inchul Choi in APTA material 2 years back, they saw that the difference between a very ductile and a very brittle glass is about 20 atoms, and this is round about the same number. So even STC sizes are not changing. So that now we are posed to the question, how do we explain the fact that without any change in yield strength, why is there a higher propensity for shear band formation in glasses which are annealed at a higher temperature? So we moved to the model developed by Lee, Packard and Shu recently, where they have used the STC model and modified it with the free volume as a state parameter. As in, if you have an initial free volume, amount of free volume, its increase will be proportionally less compared to the original existing free volume. And then they incorporated this in the equation with a free volume barrier reduction function, as in with more increase in free volume, the energy barrier for the STC to occur will keep reducing, which is very, it can be expected. Right? So this term represents your free volume term, right? And then this is your normal, STC. So we have this modified Argon's barrier equation, to get a free energy barrier for the motion of an STC. So the idea we used is we started integrating the energy barrier of an STC over time periods where we consider only the initial free volume to the final free volume, which indicates the level of percolation that STCs can undergo. And this has been suggested as 0.4, and also simulation results by Shu and Lee and Shu show that this is around the same value where shear bands start forming. So using this integration, we can figure out the energy barrier for an STC by integrating the above equation. And we found that although the initial activation energy barrier for STC operation on the glasses are very similar, as your shear band forms, the alloy which has got the highest temperature of annealing, or rather the alloy which has got the highest initial free volume, has the lowest barrier for activation of the shear band, which is what matters. And this is why, because of higher free volume, you have higher propensity for shear banding and hence higher fracture toughness. Okay, so this is the conclusions of the topic as thus, that this is the first time that we have not used elastic parameters but rather plastic parameters to describe what is happening in a metallic glass that leads to better shear band formation, which ultimately leads to better fracture toughness. Now we move on to brittle fracture, where we will see that we are going to move away from the topic of shear bands for a while, because in ductile glasses we see, in the case of bending, there are a lot of shear bands which are formed, but when you immediately anneal it, this glass has no shear bands but it fractures from particular plane. There is also a drastic difference when you consider the fractography of both the cases. Here you see a vein pattern at the order of microns, but when you look at a brittle glass, you see all the features that have been described are macroscopically flat, as in the micron scale. You can never see any feature, but when you go to the nanoscale level, you see similar vein patterns or patterns like this. So there are some nano trenches which are formed on the surface, which is pretty different and unique. And we are attempting to study how these features form and the brittle fracture mechanisms in the engine. So what we did was we took an alloy, annealed it really heavily. I mean, we annealed it for 24 hours, and we ensured that it was perfectly amorphous, and then we broke it in a fixed grip configuration using a 4-point bending fixture, and we see the fracture surface. So our whole identification process of the mechanism depends on post-facto analysis, and we saw that there are various features which are formed. One is you have regions where you have extending river patterns. Apart from, when we move away from that, we see a pretty flat surface which has got, it looks like a mirror surface almost. I mean, it's really shiny. And then after some point, you see something called a crack arrest line owing to the fixed displacement condition. Now we will study aspects of fracture, which is crack initiation, crack growth, and the micro mechanisms using these features. First we go to crack initiation. So at the center of the notch front, this is your notch edge, you see a circular feature like this. And this particular feature is only found in metallic glasses, and this is pretty featureless. This indicates that if there is a particular featureless area, that you should have something which is undergoing cavitation, right? I mean, it expands to a level and then it pops up. So we believe that there is some kind of a cavity which forms after critical amount of stress, and this forms slightly ahead of the crack tip because of notch bending, ahead of the notch tip because of notch bending, and then it leads to the onset of crack propagation. This also indicates that in brittle BNGs, the fracture is very different from that of ductile BNGs, since it is based on a stress-based criteria. Okay, I haven't described ductile BNGs here, but okay, I'll come back to that in the question and answer session. Now, this occurs also in center of the notch because of the large amount of triaxiality which exists. And now, moving on from crack initiation, we look at aspects of crack growth, and you see that there are these spider web-like patterns which extend from the notch tip. So this is your notch edge, and the cavity at the notch edge, and they form these patterns. And the patterns become more and more regular as we move away from the crack initiation point to the specimen edge. See that they become nanotrenches. And we want to see what are the characteristics of these nanotrenches. And then we did AFM studies. So AFM on this, that is, we found that these peaks have a very regular pattern, very regular sinusoidal pattern, which has a definite period. And then using Fourier transforms, we were able to see that across these correlations, the period is around 77. I mean, it varies from 79 to 71, but it remains approximately equal to 77 nanometer. And the average heights of these correlations, of these trenches, is around 10 nanometer. What can we do with this? This has already been found by researchers before, but we find a very new feature called Wallner lines. And these Wallner lines are nothing but a parallel set of lines which were first found in glasses in 1947, and these are generally used to estimate crack speeds. Now, how do Wallner lines form? There is generally a source which or some impurity which then interacts, which sends out sound acoustic waves or matter waves, which interact with the crack front and produces a loci of points which constitute the Wallner line. And we can use some kind of geometry to evaluate the crack speeds at different points. So that's what we have done. We have evaluated the crack speeds along the surface, and we see that till a particular point the crack speeds saturate to, the crack speeds are very uniform. It's around 791 meters per second. That is around 1/3 of your shear wave speed, and then it drops drastically to 0 at the crack edge point. Using this data and the fact that there is a temperature rise ahead of the crack tip, we will do the following analysis. We will look at the proposed mechanisms and the plausibility of them occurring in brittle metallic glasses. So the first mechanism which was suggested popularly by many authors was the Argand-Salama fluid meniscus instability criterion, where they say that your crack tip or your notch tip will act as a meniscus, and if this meniscus has some kind of an instability, owing to some kind of hydrostatic suction gradient ahead of the crack tip, this instability will grow after a critical length. So this Argand-Salama instability theory would predict that if a fluid-like layer, because of temperature rise, as you had seen there is some kind of temperature rise in the previous slide, because of some temperature rise, this becomes a fluid-like layer within a plastic boundary, and this plastic boundary is of course decided by the material property of fracture toughness, which is related to your crack tip opening displacement. So the length scale here was your crack tip opening displacement, which is a material property, and they suggest that this meniscus will grow till the plastic boundary, and then this new surface will become another notch tip, and this process will continue. They also say another thing, that these perturbations not only extend in the front direction but also extend in the sideways direction, which is why you have the formation of nanotrenches. Now the problem with this theory is that in the Argand-Salama meniscus instability theory, you would have, if you were to have a meniscus, it would only grow because since your suction gradient is only in the direction ahead of the crack tip and not across your crack tip, your fingers, your nanocorrugations cannot extend along the Z direction in this case. So it can only extend in the front direction. So you would have something like this. As we see in ductile fracture, you will have fingers forming instead of forming trenches which are parallel to the direction of, perpendicular to the direction of crack growth. So this is one of the issues. There are some other issues which authors have, other mistakes the authors have made. That is, they have used some wrong values which should not be used in the original Argand-Salama instability equation. And the biggest problem is that we need to consider the time scales at which this is occurring. Now, if you look at the meniscus instability, you are assuming that a fluid layer is actually moving under a gradient, and this movement should be within a particular time scale. That is, if you consider so we will consider the relaxation time scales that the glass has, and using the velocity obtained using model lines and the wavelength, we know that the crack has to move from one wavelength, from one corrugation to the other corrugation in 10 to the power minus 10 seconds. But the relaxation time scales that are required for the glass to melt and move and relax is actually too large considering the time that is required for the single corrugation to form. So hence we can immediately say that this theory is slightly doubtful. The other popular theory is that people suggest that there is snap cavitation which occurs directly in front of the crack tip, and this cavity slowly grows and links up with another cavity owing to notch blending, and then finally these cavities propagate in the forward as well as the transverse direction. So this happens because in materials you would expect materials which do not show high degree of plasticity. When your hydrostatic stress increases beyond a particular point, the material can easily cavity. No reasons have been specified in the literature, but this has been observed to happen in a lot of materials. So this was one of the justifications for this nanocorrugation phenomenon. But if we were to consider this phenomenon to be occurring and plasticity to be occurring inside this cavity, we should have time scales that are very similar to what we had expected or what we had deduced from the crack velocities as well as the wavelengths, which was around 10 to the power minus 10 seconds for a nanocorrugation to form, which would mean that your beta relaxation frequencies or the things that induce plasticity should be around 10 to the power 10 hertz. But here you see that they are only about 10 to the power 4, 10 to the power 6 hertz, and thus we immediately start doubting whether this actually occurs. The other part is that if a cavity has to grow, what are the time scales? We are now looking at a diffusion problem wherein atoms have to move from one area to the adjoining area. And then let us just consider for the case that we consider the midpoint of the cavity, a section of the cavity, and then we assume that it has to move away from the top to the sides for that to grow. And if you look at that, we see that the time it actually takes after calculation is around 120 seconds. Even if you raise the temperature to Tg, this is the temperature, you get time scales which are around 10 to the power minus 2 seconds. But we are talking about 10 to the power minus 10 seconds for a cavity form, and that never happens. So there is a second doubt regarding the formation of cavity. The third thing is, if you have cavitation, it is a very stochastic process. It will not occur in a series, it will not occur in a plain fashion or in an organized way. You always see cavitation occurring at random points, and there is an attached degree of stochasticity. But here we see continuous patterns extending around the fracture surface. So there is again huge amount of doubt which can be pointed against this non-wide correlation theory. Alternatively, and this has not yet been substantiated, but we suggested that we just consider the amount of heat diffusibility within a particular zone under the notch tip. We just want to consider it, and we see that using the heat diffusion equations, we see that it extends up to 80 nanometer in front of the notch tip if you are applying stress, and this extends up to 80 nanometer, which is very similar to that of the height of the corrugations. So the heat diffusion zone is only extending up to the height of the nanocorrugations. So one particular way of justifying it is possible that you're ahead of the notch tip, when you apply stress, there's a lot of your heat increases, your crack starts propagating, heat increases, and since your crack is propagating with a high velocity, it's a dynamic crack, and it will release a lot of material waves which can actually interact with the fluid medium which is formed in this layer, and that fluid medium can influence wave-like patterns. This is one of the mechanisms which we want to actually suggest and also investigate in future, because such studies of matter waves on liquid mediums, on fluid mediums, have not yet been done. But nature has shown that such things can occur. For example, ripples on still water, they look very similar to those of correlations. Even if you see a solidified stone from the molten state, these are probably these patterns seem to be very similar to what we see on the fracture surface. So these are some of the insights we can apply and probably study and see how fracture can be controlled in brittle glasses and how these nanocorrugations can be explained. So, in summary, we have actually tried to consider all the theories that have been proposed before in brittle fracture, and we have introduced the idea of calculating the crack velocity, through which we have been able to evaluate the validity of these criteria. And we see that none of them, for now, seems to be completely justifying the mechanisms of brittle crack propagation. Now, we move on the last part of my talk, and I should talk about another way of toughening glasses, which recently became popular, and which is you introduce a second phase, a ductile phase, and this ductile phase actually promotes shear banding, which improves its tensile integrity. Earlier we saw that if you pull a BMP rod in tension, it will break catastrophically without any sign of ductility. But when you add a second phase, this can actually nucleate shear bands, deflect them, multiply them, and even allow them to work hard. So this has had beneficial effects. But as you can know, as you can see, if you add a ductile phase, it will immediately lower its yield strength. So you have to compensate for strength, but you gain a lot of ductility. Now, so a lot of these alloys have been developed after they were discovered by Douglas Hoffman and William Johnson's group in Caltech, but they always had a problem of optimization. Now, you can add a lot of ductile phase, and you can expect the ductility to be very high. But then you are compromising on one of the strengths of BMGs, which is its yield strength, high yield strength. To optimize that, we now start looking at two different classes, metallic gas composite, one with a lower volume fraction of 50% and one with a high volume fraction. And you see that the compositions are obviously different, but they will have a dendrite which has got this structure, it's a BCC structure, and we have a matrix which is zirconium rich. It doesn't have any beryllium. The difference is we are now going to study the effect of volume fraction, and we are now going to process these alloys by different techniques. Now these techniques will impart a very different microstructure, as we are going to see, and this we will see how the microstructure plays a role in controlling the tensile properties. So first you see that there is a treatment called forging, and forging actually produces something called something like a bimodal structure. So you have big dendritic structures as well as very small ones. So in both DH1 and DH3 alloys, DH1 is the one with the lower volume fraction, and DH3 alloys you have a bimodal distribution of dendrites. Then you go to something called as suction casting, where your structure is very fine. So this is the micron scale. They are actually nanoscopically small. So you can see that the distance between the two dendrites are very small. Uniform structure, but the length scales are very small. Dendritic sizes are nanometers. Also the spacing between two dendrites is very less. And third case, where you have a core structure with unimodal distribution of huge dendrites. So you have unimodal distribution of huge dendrites, unimodal distribution of very fine dendrite, and a bimodal distribution. So these three alloys are what we are going to study, and we are going to see the effect of volume fraction as well. So the first thing we do is we do a tensile, and in the DH1 alloys, as obviously, you can see that the yield strength is higher in all the cases, whereas in DH3 alloys, the yield strength is universally lower. So immediately the effect of volume fraction comes out of this, and you see, if you see the ductility, and I would like to point out here that the ductility of the forged alloy seems to be the best in both cases. Or rather, in fact, if you just remove this suction test alloy in both the cases, you will see that the forged specimens in both the cases seem to show the best amount of ductility. But I mean, if you consider, or rather I would say straight to failure, if you consider this, the performance of an induction process is another process we use, and that are augmented in the case of high volume fraction alloy, high volume fraction dendrite alloy, you see that they have good ductility, yes, in general, but there are other issues that we mentioned here, which is you see that immediately drops if I'm sorry. Yeah, so one thing is you see that the rise in your strain hardening is highest for your force errors. And your strain to failure is, no, I'm really sorry, yeah. So I come back to it. So the point is, your strain to failure is very similar in all the cases. That is, if you use a large amount of volume fraction, which is around 70% dendrite, you will have a strain to failure which is around 79%. And this shows that your microstructure is not really controlling your ductility in this case. There are some variations in your yield strength, but ductility is not sensitive to microstructure in the case of alloys with high volume fraction of dendrites. But when you go to DH1 alloys, you see that immediately there is a difference. Now, if you look at the ductility, for the forged alloy it is 9, whereas for the arc melted alloy it's almost 1/3 of it. And this effect also is pronounced if you look at the amount of work hardening it undergoes. If you see the suction casting alloy, it undergoes very negligible strain hardening. Whereas if you consider the forged alloy and the arc melted alloy, they undergo reasonable amount of strain hardening. So you see an increase in the yield strength at the UTS, we have high stress. So till now we see that there is a definite difference when we consider the microstructure in DH1 alloys, and that is the change in ductility. Now we look at another aspect and try to see what is it that is changing in these alloys, and we start looking at the hardening rates, G sigma by D epsilon, and then we compare them for all the alloys, and then we plot it with the plastic strain before making. You see that alloys which have the highest initial hardening rate also show the minimum amount of ductility. So the alloys like the forged alloys and the arc melted alloys have reasonable amount of So the forged alloys in both the cases show very good amount of true plastic strain film making. But when you consider the arc melted alloys of DH1, because there is a microstructural influence, they have very low amount of ductility. So if you increase the strain hardening rate, your ductility actually goes down, is what is the crux of the story. And this, if you see, is very different from that of crystalline alloys, where in crystalline alloys, if the strain hardening rate is higher, you generally encounter instability at a later point or at higher strain. Now the mechanisms for why this is happening is that if you have a larger dendrite, like in the case of arc melted alloys, now this can actually accommodate a lot of strain hardening. Okay? And if you have a smaller dendrite, it undergoes higher strain hardening rate, but the amount of strain hardening it can take is much lower. But by using the combination of these, which is the bimodal distribution in forged alloys, you can actually get the combination of higher strength as well as good amount of ductility. So this is our idea. I mean, we look at how this microstructure actually has influenced the various tensile properties, and we look at the optimization that has been obtained by using a distribution which has got neither too big dendrites neither too small. That is the crux of the issue, and these are the key observations that we make in the work, where we decide that the forged sample or the forging treatment is the best process to be used for metallic glass composites. So I would like to finish my talk with this today and acknowledge our people. Thanks, man.
Before I let you all ask questions, so the procedure is now Lakshminarayan is open to ask all any kinds of questions. This is the last chance. After that, he will be a doctor and he can't ask questions. Then the exam will continue in camera. That means me and Mr. Bharmare will be there and we will ask questions. Before I open the floor, I also want to say that when somebody like me, an advisor, looks at this, we look at a big picture, and the student, because he's so involved, he looks at a lot of these details. Not that we ignore the details. So nice thing is, I do not know whether it has come across or not. Each of these problems that he talked about, and he talked about 3 different kinds of problems. One is toughness, plasticity, correlation, and the next one is brittle fracture, and the third one is composite. So in each of these, there is a big picture issue. What kind of correlations exist? For example, in the composites case, what kind of microstructure is desirable to get optimum combination of properties? So that is something that we actually was able to get to in a significant sense in these pieces of work. So with that overall view, I'm opening for questions. This last part is done with Kathy Flores in collaboration with a little bit of Kathy, and she was still at Ohio State.
Right. Okay. And then I'm obligated to ask one question.
Definitely. That is why I was prompted.
So you showed us very high tension compression asymmetry.
Tension compression asymmetry.
Right. So then, what's the current state of our understanding why you have such a huge tension compression asymmetry?
So
for magnetic glass.
So are you talking about the
Ductility.
The ductility. Okay. So why is it different?
Right.
So okay. So if you consider the case of tensile deformation, here you have your specimen is being pulled and it is susceptible to instabilities, which is if you so here you can have a lot of instabilities. For example, you can if there is a flaw, that flaw will open up, right? And it will immediately, or there is a defect or some kind of a flaw at the surface or within the specimen, it tends to open up because you are doing a tensile deformation, right? I mean, so but in compression, if you consider the flaw, if it is sitting somewhere, and you try to compress it, the flaw tends to close up, right? And it doesn't grow.
No, he is asking in the context of metallic glasses. Why do you get tension compression asymmetry as in?
But are you talking about the yield stress here? Because that. Yeah, he's talking about the ductility that is obtained. So the ductility part is because in compression, your shear bands actually start. So your specimen is like this. The shear band forms. Your specimen, when it gets compressed, the shear band is not able to completely run through the specimen. Right? That is because the spaces are rubbing. There's extremely high amount of friction, and also when the faces, the shear band faces are closed, there is a fluid there which forms.
Shear band is not a crack.
Right.
It's not a crack. It's not a crack.
Shear band you can have the fluid, as you show some of the evidence, you have the fluid layers.
Right.
And then under compression tension, what's different? You have this
Smith
factor which shows this maximum stress in this case.
The Smith factor.
When you load something, you have a maximum stress. It's probably
Right.
40 degrees.
45 degrees. Yeah.
But not. Maybe see, there is 2 aspects to tension compression asymmetry. One is the yield stress, and the tension compression asymmetry in the yield comes because the plastic flow units, the STCs, necessarily require dilatation. As we talked about argon model, for example. See, the way I always illustrate it is, think this is as the STCs, a cluster of atoms that want to undergo a shear transfer. So, but there is a matrix, right? So if I want to twist this arm, this like this, I need to necessarily expand the matrix. The dilatational component is what gives you the tension compression asymmetry in yield. But your question is about ductility. Now, what happens in tension is when you have a shear band, there is no microstructure, so there are no barriers. So it's just goes unhindered. On the plane, once it forms, it goes all the way. But in compression, the stress state is to sort of prevent it from going, right? So it can't go off for long distances. So you necessarily force it to have multiple dislocation, multiple shapes. But if you take a proper metallic glass, even in compression, you don't get a huge amount of ductility. Right? Yeah, it's basically what happens is some sort of plasticity comes in, and then it makes the stress state not uniaxial anymore.
Okay, so the inside the stress state is much simpler compared to
yeah. I have been always a proponent that you should do a tensile test.
Yeah.
I hope you know the literature. Lot of compression test data were patent reported in these things. But, in fact, you should only be doing tensile tests on these materials.
Because in compression they also undergo something which is very similar to the Potelin-Glishakier effect. And they have the serrations. That's because this stick-slip phenomenon also occurs, but that doesn't occur in tension. So it's a very different picture when you consider the tension and the compression test.
Any other questions? Has he bought you out or what? Nobody is asking me. Promise you a partner. With Lakshminarayan, it's entirely possible. Any questions? If not, thank you very much for coming.